Hi, and welcome to Module 2 of Lecture 6. In this module, we're going to discuss higher order derivatives. An higher order derivative is a derivative that's more than just the first derivative. It's the second or third or fourth or fifth or so on, which, as we'll see in a second, basically means taking a derivative, then taking it again, and possibly again, and so on. Before we go into that, though, it's good to ask, why are we doing that? So let's go back to the example we did before. We discussed how looking at a function and how the function goes from increasing to decreasing means that at some points, say over here, the slope of the function is 0. Now, the slope of this function is also 0. But without knowing anything more, we can't distinguish a 0 slope up at the top over here from a 0 slope on the bottom down here. That's an issue because the first one on the left is a maximum, a local maximum, and the second one on the right is a local minimum. We might want to actually distinguish between those two things. To do that, we need to know more about the function than just where the slope is 0. We need to understand how the function curves. If it curves like this, which is called concave, as we'll learn in the next module, then it's going to be a maximum. If it curves like this, which is called convex, as we'll learn in the next module, it's going to be a minimum. So the curvature of the function can help tell us whether or not we have a maximum or a minimum of the function. But we haven't yet talked at all about how to understand curvature of a function. That should be equals. And that's where higher order derivatives come in. So, what are they? A higher order derivative is just repeating the action of a derivative. So before we had several bits of notation. There was d by dx, there was, so df by dx, there was f prime, there was this thing, if you remember from the beginning of our calculus lectures. And if you have a partial derivative, we talked about it very briefly, it was this, or this. Okay. Take higher order derivatives, there's actually a pretty common way of doing so. For the second derivative, the notation looks like this. It's a little confusing because the top two is between the d and the f, and the bottom two is next to the x. The operator itself looks like this, if you want to apply it to f. For the prime, you just add a prime. For the other ones, you do the same too. So it looks like squared. Now this is not squared, even though it looks like squared. This means second derivative. So be careful. In general, you're not going to be squaring derivatives anyway. You don't square an operator by and large, you do it again. Although I should say that it has a lot of the same effect of squaring, as we'll get to in a second. For higher order derivatives, you continue this pattern. So if you have an nth order derivative, you stick an n there, an nth order one over here, an nth order one over here, or an nth order one over here. In all cases, you're continuing the pattern. The one difference is for prime. If you have an nth prime, it kind of breaks down into two different ones. The most common one is that notation, which means the nth derivative of f, the parentheses on top are to indicate that it's not f to the n power, it's actually the nth derivative of f. Sometimes you see Roman numerals, that makes it hard to do that for a general n, so you usually see this one, but for the fourth derivative you will occasionally see FIV. But again, that's pretty rare. Usually you see this one. Okay, and so that's the notation. Now what are they? Turns out what they are pretty straightforward. They're just repeating your action of differentiating again. So let's take one. Let's try a function. Nice polynomial function, x cubed minus 2x squared plus x minus 1. Okay. The derivative can be obtained noting that the derivative is a linear operator, so we treat each one separately and use the power rule. So for the first term, we pull down the 3, multiply by x squared because you're subtracting 1 from the power. The next one, we pull down a 2 from x squared, leaving us with x. Multiply 2 times 2, you get 4. The next one, x to the first, is just 1. The the derivative of x to the first is just 1. You pull down the 1, subtract 1 from the exponent to get 0. X to the 0 is 1. So that's 1, and the derivative of a constant is 0. As you practice more of this stuff, you'll find that differentiating these kind of polynomials should get faster and faster and faster. If it's not getting faster, go back to the lecture corresponding to lecture 4, corresponding to how to take derivatives, and practice. It'll get faster pretty quickly, you'll find. Right. So that's the first derivative. What about the second derivative? Well, you take the derivative of the first derivative. So you pull down a 2. 2 times 3 is 6. Here the derivative of x is 1, so that's just minus 4. So all the second derivative is a derivative of the first derivative. You take the original function and differentiate twice. And by that I mean differentiate once. What you get from that, you differentiate that. If you had a third derivative, you differentiate again. Here the derivative of x is 1, so that's just 6. If you had a fourth derivative, you do it again and get 0. And the fifth and the sixth and so on forever would also be 0 because you ran out of x's. You find for polynomials, the only terms that are going to matter are the ones that have a power high enough to stick around. Right? So we started off with x to the third, so there'll be a non-zero derivative potentially in the third derivative, but nothing more than that. If you had a different kind of function like e to the x, well, the first derivative is e to the x, the second is e to the x, the third is e to the x, and the fourth, and so on forever, is also e to the x, so there's it never vanishes. You can, however, get things exploding. Let's say f equals x e to the x. Well, the first derivative using the product rule equals e to the x plus x e to the x. And if you're not sure about that, go back, try it, pause here, go back, try it, use the product rule, make one function x, the other function e to the x, use the product rule, which again is f prime g plus f g prime. Again, now you have two terms to deal with. So you have e to the x plus e to the x plus x e to the x equals 2 e to the x plus x e to the x. If you were to do it again, you get 2 e to the x plus e to the x plus x e to the x equals 3 e to the x plus x e to the x, and it'll get bigger and bigger. So doing these derivatives over and over again can either make your thing smaller or make it bigger. It depends on the function itself. There's no general rule for that. However, the practice is easy. You just repeat the derivative over and over and over again until you're told to stop, effectively. However many derivatives you have, you take a derivative up to that point. Second derivative, you do it twice. Third, you do it 3 times, and so on and so on. Then that's actually most of higher order derivatives. So a couple more things related to them, though. One is that each one of these derivatives has a meaning, although we don't tend to think about the meaning very much past the second one. The first derivative we know already tells you the slope of the function at a point. The second derivative tells you the local curvature of the function at that point. Is it concave? Is it convex? Again, we'll define these more carefully in next module. But what's the local shape of that function? What's the curvature? The third and higher derivatives give you more detail about the curvature. For instance, what's the difference between the functions x squared and x cubed? Well, x squared looks like this. This is convex everywhere, meaning, which will tell you, as we'll see later in this lecture, that the bottom point here is a local, and global in this case, minimum. The important point here, though, is that the curvature is the same everywhere. It is always convex. In contrast, consider x cubed. X cubed is concave down here and convex over here. The point in the middle, as we'll see shortly, is a point of inflection. It's the point at which you change from being concave to convex. This point is neither a local minimum nor a local maximum. Has different character than these points. We can see the difference here. This function here, x squared, being globally convex everywhere, right? The first derivative is 2x. So if this is 0, which it will be for x squared, then when x is negative, you have a decreasing function. The slope is negative. When x is positive, you have an increasing function. The slope is positive. And the second derivative is positive, indicating a convex function. What about this one? Well, the first derivative of x cubed is 3x squared. It's increasing everywhere, right? No matter what x is, that's positive, so it's increasing down here, and it's still increasing up here. The second derivative is 6x. If this is 0, when x is negative, the function is, this is negative. If the second derivative is negative, meaning you get a concave function. And when x is positive, the second derivative is positive, meaning you get a convex function. We'll do more of this in the next lecture, but next module rather. But there's even more information encoded in the derivatives. The third derivative is 6. That's positive. I'd like to help tell you how you change from concave to convex. If you had more derivatives for more complicated functions, they would encode even more information about the function. In fact, it turns out that if you include all derivatives going on forever, you can actually encode all the information about a function. This is called a Taylor expansion, when you encode all the information about a function. So, what's a Taylor expansion? Well, if you take a function f, and you want to understand its behavior around some point A, turns out you can do this. With the same pattern forever. That's going to end up equaling the sum from n equals 0 to infinity of the nth derivative, where the 0th derivative is just the function itself, n factorial, where 0 factorial is equal to 1, times x minus a, and this is evaluated at a, this derivative, to the n. This is the Taylor expansion around some point A. This can be occasionally useful, it comes up pretty rarely in social sciences, but it can be occasionally useful as a way of approximating a function near a point. Because n factorial gets really big really fast as n gets bigger, these terms tend to get smaller and smaller very quickly. And you can often approximate a complicated function by a few terms. In a lot of stuff we end up doing, we actually end up approximating whatever more complicated model we have in our head as a linear model, particularly in statistics. And the Taylor expansion gives us some warrant for that, in that you can approximate a more complicated function near a point with some degree of accuracy by a linear function given by the first term here, as long as the difference between either the derivative is very small, so the curvature is not very strong, or the difference between the points is pretty close, so you're pretty close to the original point you're approximating. So again, you can approximate pretty well close to a point by the linear term, as long as you're either really close to the point or there's not much curvature around that point. Okay. And if you want to go to the second derivative, you can approximate even more functions more well, and so on and so forth as you add more derivatives. So this can be useful to try and expand things. You've actually seen this before in our definition of the exponential function, e to the x. Let's take e to the x around 0. Well, the first term is 1. E to the 0 is 1. The derivative of e to the x is e to the x. So, and all derivatives are e to the x. So when you plug in 0 to all of them, you get 1. So you have x over 1 plus x squared over 2 plus x cubed over 6. And this was exactly the definition of the exponential function that we used in order to compute the derivative of the exponential function earlier. So you can use this Taylor expansion to expand out functions to make them into polynomials that might be easier to deal with in some cases. Okay. So that's almost everything I want to talk about here. And this doesn't come up very much, but it's nice to see it. It's nice to understand what it is if you ever see it in practice. Okay. Last thing is, in game theory in particular, you sometimes see these functions classified in terms of how well they can be differentiated. So we will see a function of class C0 meaning it's continuous. The C means continuous. If it's C1, that means it's continuously differentiable. That means you can take a derivative of the function, and that derivative is continuous. C2 means you can have a second derivative be continuous as well, and so on and so forth for any n. You often see the assumption that functions that we deal with in game theory are of class C2, meaning that they have a second derivative that's continuously differentiable. Rather, the function is continuously differentiable twice, or twice continuously differentiable, which helps you be able to maximize them because you can use the tools we're going to do later in this lecture to maximize the function using the first and second derivatives. Okay. But that's it for this stuff. In the next lecture, we'll do one more thing that could be important, which is concavity and convexity, before moving on to start getting to the meat of optimization. Thank you very much.